Good morning. Another day, another chapter. So we had those two chapters on rotational dynamics. Those were tough. There was a lot of work there in really working through all of the rotational motion. We're going to move on to something that's going to have a little bit of a different feel. We're going to use some of the stuff that we learned in those last two chapters. But it's going to be different. Chapter 12 is looking at static equilibrium. It's kind of the first half of the chapter. Now, static equilibrium, they've got a nice picture of the Bay Bridge here. That's a really nice shot. And, you know, when you build a bridge or you build buildings like this, the intention is that they don't collapse. And so statics deals with, for a building that's static or a bridge that's static, something that is meant to stay there, how do we analyze all the forces and make sure that there's enough support that these structures will remain solid, that they'll remain sturdy. So here are the topics, and let's look at an example here. So it says, here's an object, there are forces acting on it, but there's no net force. So this brings us back. This net force idea is going to come up a lot in this chapter, and this is an example that takes us all the way back to the beginnings of chapter 4, and you're going, hey, we've done this, come on. There's a normal force. Now specifically, they got the normal force listed here, but it's really coming from all of the surface area, right? The normal force is all along the surface. And then there's a gravitational force, and the gravitational force is acting on each part of the book. The book is the object that we've isolated. The gravitational force can be placed at the center of mass of where the book is located, or the center of gravity. So it says that the first conditions for static equilibrium are that the forces all equal zero. All the forces have to cancel out. And they have to cancel out in the x direction, the y direction, the z direction. All three directions of the force have to cancel out exactly to zero. And now, if you remember, having all the forces be zero doesn't mean the object is at rest. It just means that it's in constant velocity. So we do have to have all the forces go to zero if we want something to be at rest and stay at rest. But we also, in many of these situations, are assuming that the velocities are constant as well. But the first condition for equilibrium, all the forces add up to be zero. So here's our first example. Here is this chandelier. I guess it's a beautiful chandelier. So here's a beautiful chandelier, and we are going to artistically support it, I guess. So there's a couple of cords. One is pulled horizontally towards this wall, and then another cord is being pulled up at this direction, and there's a third cord that's actually attached to the chandelier. Now it says the chandelier is 200 kilograms, and you go, wow, 200 kilograms, that's a lot, you know? It's like more than 400 pounds of chandelier that we're looking at. And so these cables are going to have to be sturdy. Now this cable is just kind of pulling everything to the side. I feel like maybe this one is doing most of the support work. In any case, what we can do is look at the chandelier. We can calculate the gravitational force. So the gravitational force would be mg, and when we calculate mg, we get 1960 newtons. Now that means that the tension in this cable pulling away from here is going to be 1960 newtons. We're going to have a force diagram on the chandelier itself. So the tension there is upwards, 1960 newtons, and so the tension downwards on this location. So this is kind of interesting. What object is it that we're isolating here and analyzing the forces? And it's not really an object. It's not so much the chandelier, although we have to do a force diagram here too. Kind of the central part of the problem is making sure that FB and FA and this tension, 1960 newtons, that they all cancel out exactly. So let's take a look. and see how that might work. So again, what we can do is we can take the chandelier pretty quickly and say there's no acceleration taking place here. That means tension equals mg. T equals mg if the acceleration is equal to 0. So that condition is right here, and since mg is 1960, it must be that the tension also is 1960 newtons. So now let's move on from that object and say, okay, we got the tension figured out. What about force A and force B? And for that, we're going to have a separate force diagram. So again, there's no object located at that junction, really. It's just a place where three forces come together, and we have to make sure that all the forces around that point add up to be 0. Let's see, so FB is easy enough. That's a horizontal force. That's just going along the x direction. And then they gave us this angle theta. They said theta was equal to 60. So I'm going to take FA and draw in the angle. Now I'm hoping, yeah, that angle looks like the right one. So these are opposite interior angles. It looks like that is also theta. So FA can be divided into two components. And the vertical component of FA is going to be FA cosine theta. And FA cosine theta needs to match, FA cosine theta is horizontal and needs to match force B. So force B is equal to FA cosine theta. So we're using the conditions of equilibrium. So, and I hope this is like, you know, you're thinking, well, we've been doing this for a long time. So those are the conditions, and we're taking all the forces in the x, setting them equal to each other, and then here we took all the forces in the y and set those equal to each other. So in the y direction, we're going to need FA sine theta and set that equal to the tension, where the tension we determined was equal to mg. So T and mg have the same value. So this is actually enough to solve the problem. So let's see, FA is equal to, or FA from here, is mg over the sine. That is 2263 newtons. And then FB worked out to be 1132. Now, when we solve these problems, these equilibrium problems, these statics problems, what's always interesting to me is to stop, you know, once we've done the numbers here, and go, really? So this was 1960 newtons. I would have thought that this force pulling the cord over in this direction wouldn't have been especially big, but that's 1132 newtons. That's a pretty good sized force to be able to pull this over. Now it is pulling it over, that's a 60-degree angle. It's not pulling it over a terrible lot. But look at force A. Force A is even bigger. So by supporting this object with these two different chords, each one of these chords has well, FA has much more tension than, well, not, I guess some more, has more tension, significantly more tension than T did. So FA is even bigger, and FB is no slouch, right? FB has a fair amount of tension in it too. So it's kind of fun to analyze these, and sometimes some surprises come up. The tensions turn out to be, I'm going to say in most cases, larger for me than I would have expected. Anyway, I hope this is pretty straightforward and you're thinking, oh, this is going to be a good chapter, because it can be. This chapter can actually be a bit of a break. I think 10 and 11 were maybe a bit more challenging. There's another condition for equilibrium. It turns out it's not enough to say that the forces are equal to 0. Take a look at this meter stick, or ruler, I guess, that they've placed on this table. And what they're going to do now is they're going to spin this ruler on the table by exerting a force here and a force here. Now, since the forces that they've set up, they're equal in magnitude and they're opposite in direction, that's a 0 force. So this meets condition 1, condition one, first condition for equilibrium, was that all the forces cancel out. Well, they do. But the forces aren't lined up with each other. And that means that the net force is zero, yes. But what about the net torque? No. So it's not enough to look at forces. We have to establish that torques are also adding up to zero. If there's a net torque, like there is in this case, this thing is going to start to rotate. So this is why we had to do chapters 10 and 11 before coming back and doing statics. We had to learn about what torques are, because torques are going to be just as important, we're going to find out in most problems, more important than analyzing the forces themselves. So being able to calculate torques is going to enable us to solve a lot of these static equilibrium problems. So here's another example. Here's a lever, and kind of a classic physics problem. Here's a big heavy rock, or engineering problem, right? This is civil engineering right here. So here is a big rock, and what we want to do is move the big rock. Well, the big rock has a lot of mass, and it's got a gravitational force, which should be coming from the center of mass, not from the side over here. So the gravitational force is actually operating here. Now what this person is trying to do is they're trying to exert a lifting force on the rock so that it moves. And the way they're going to do that is they're going to take this rod and they're going to push it underneath the rock, and then they're going to create a pivot so that there's an axis right there around which they can exert a torque. Now what's going to happen is that the torque on this side is going to be balanced by the torque on the other side. Now the torque on the other side is coming from the force mg. Once we've lifted that rock up off the ground, the torque is going to be given by mg times little r. This is the axis of rotation, and to calculate a torque, we need to look at the force, and we need to look at the lever distance. So that's what we've done on this side. So that's going to become mg times the lever distance r. And I wanted to emphasize the lever distance with the parentheses. Now, on the other side, this person is pushing down, right? They're pushing down with force F. And there's also a lever distance on this side. Now, if the lever distances were the same, if little r and big R were the same distance, then this person would have to push down with the same force that balances out mg. But the lever distances are different. And so since big R is bigger than little r, this person can apply a counter torque, a torque just as large as the gravitational force, but not push as hard. So the rock could be really, really heavy and have a really large gravitational force, but the person, if I take these two torque expressions, mgr and F times r, set them equal to each other, and then solve for F, this person does not have to push with mg amount of force, and the person has to push with mg little r over big R. And if you can make the lever distances really big, if we can make big R really large, then we can, the person can lift this really, really heavy rock. You know, if big R is 10 times as big as little r, then this person only needs 1/10 of the force to lift the rock. It sounds like, isn't there some kind of a rule in physics that you have to push with as much force as you're trying to create at some end? And it turns out there's not. With torques, you can actually get more force. You can get a force multiplier by adjusting lever distances. So that's pretty handy. Now, here's another example. This is actually a teeter-totter, and I think there's a missing slide here. There are two kids on a teeter-totter, and what we've got is that the kids are different distances. Here's an axis of rotation right here, and the kids have moved different distances from the axis location. Now they're ignoring the teeter-totter itself, or another way to look at this is the teeter-totter is built so that it's balanced. So the teeter-totter itself doesn't favor coming down on one side or the other. And so what we're trying to do is we're trying to place these kids so that their masses and the lever distances will balance out. So here's the axis, here's where the kids are located. And then what we're going to do is we're going to come back and look at the lever distances. So for this teeter-totter to stay balanced, M1G equals M2G, that's not the condition. It's not the condition that the two gravitational forces match. The condition is that the torques will balance. So it's not enough just to look at how much mass does each kid have. You have to adjust the lever distances. So what we want is the torque created by, kid number 1 sitting on that side, and the counter torque, or the opposite torque, created by the other person on the other side. We want to set those equal to each other. Now it turns out that the gravitational field of the Earth, the little g factor, it goes away. So that's always a sign that this is going to work on any planet we go to. So if you've placed the kids at certain locations based on Earth's gravitational field, when you take the kids to Mars, it's going to work the same way. Gravitational field is going to be smaller, but the balancing point is going to follow the same set of rules. So the g's drop out, and we can solve for R2. All the other information was given in the problem. I got to track the slide down and get that added back in. You can imagine, though, this is just a couple kids on a teeter-totter. All right, and so R1, 2.5 meters, and then I put in the masses that they gave me for the kids. They said that one of the kids is 30 kilograms, one of the kids is 25 kilograms, and R2 worked out then to be 3 meters. That's a pretty good size teeter-totter, right? 3 meters and 2.5 meters, that's like 9 or 10 feet that these kids are away from the center, so it's a pretty big teeter-totter. But balancing torques, that's the name of the game here. So with statics problems, what we do is we select objects, usually one object at a time, make a free body diagram, and show all the forces. So we've done that before, right? And in some respects, this chapter is maybe easier because there's no accelerations going on. We're not going to be dealing with accelerations when we're looking at these static equilibrium situations. Choose a coordinate system and resolve your forces into components. Write down the equilibrium of forces. Choose different locations for torque equations, and then solve. We'll see all of these come up. There they are. Sorry about that. So here are the kids. The kids are okay. I think is the phrase here. So the kids are okay. This is 3 meters. Oh no! We did. This was X. This is what we were solving for. There are those kids. Here is that 30 kilogram kid. Here is that 20. I think the 25 kilogram kid looks bigger than the 30 kilogram kid. For some reason, that kid's denser than this kid is over here. I think. I don't know. Anyway, so here's the force diagram that they've given us. And so here's the teeter-totter. And here is the gravitational force specifically on the teeter-totter. And since the teeter-totter's center of gravity has been placed right at the axis of rotation, the torque of the teeter-totter itself cancels out. Now there's also a normal force on the teeter-totter here. And then there's a gravitational force of the kid. Now, this is kind of shorthand notation. So strictly speaking, what we should do, and maybe I did this in my diagrams, maybe I didn't. I sort of didn't. So specifically what we should be doing is saying that there's a normal force here. N1 is equal to M1G, and N2 is equal to M2G. Now, if the teeter-totter is pushing up on the kid with force N1, then the kid's pushing down on the teeter-totter with force N1. So there's a force N1 here. Now, since everything's at static equilibrium, N1 the magnitude of N1 matches the magnitude of M1G. And that's, so we just do this shortcut. We say that the teeter-totter is loaded. We've placed objects on that teeter-totter, and whatever the gravitational force is on those objects, that's the normal force that's going to be acting on the teeter-totter. So again, this is a normal force of the kid pushing down on the teeter-totter, but we say, okay, the normal force is equal to M1G, so we do kind of a shortcut. So I drew two pictures in my defense. Now, here, they just went right in and went right to M1G and M2G, and then they started looking at torques. Okay, so I think that's it. I think that works. I hope that makes sense. Any questions at all, let me know. Here's another example. And I've got these, okay. So here's another example that we want to take a look at. There is a force exerted by the biceps muscle in this case. So here is the biceps. So, you know, let's see here. Okay, so here's the hand. And what they've done is they've placed it horizontally, and that's going to make it easier to set up our force diagrams. Now, there's a couple bones right here, right? It's like the ulna and the radius that are here, and then there's a humerus. Now, what's the central object? Because one of the ways we're supposed to solve this is look for, which object is kind of in the center of everything? Because what we want to solve for on this is, we want to solve for how much force is in the muscle. How much tension does the muscle create when we're holding an object? See, that's a 5 kilogram object. That's got to be really dense too, because it doesn't look any bigger than a baseball, but yet it's 5 kilograms. It must be gold, maybe, or lead. So here's a joint, or uranium, could be uranium, that's pretty dense. Here's a joint pushing down on the ulna, maybe. So how do we draw this diagram? Now, we're going to draw this diagram first, and then we're going to let the person actually lower their arm at a 45-degree angle and ask, now, what are the forces in the muscles at that point? And so here's my diagram of everything. I went with the forearm. So I said the entire forearm I'm going to treat as the object that I'm analyzing. And the reason for that is, look, I've got a forearm sitting here, and I've got a bone, I've got this humerus pushing down on the ulna. So I've got this bone pushing on this bone. So there's a force, I'm calling it force A, coming from that. And then there's a tension. Now I called it force B, but it's a tension in the muscle lifting up the arm. So another thing that's worth doing with these problems is stopping and kind of staring at it and going, is that right? Is that really how forces would work? So let's see if we had an object, maybe the textbook, always the textbook. So if we had a textbook that is going to sit in here for the arm, let's see, what we got to do is we got to be able to support it. Now, the textbook itself has a gravitational force. That's the gravitation acting on the forearm. And then there's a golden sphere at the end that is 5 kilograms over here right at the end. So there's also something heavy out here. Now, the way the anatomy works is the muscles are attached way back here. And that doesn't provide very much lever distance. So your muscles don't have especially good leverage when they're operating. And that means chances are the forces acting in the muscle are going to be much larger than either of these gravitational forces. So let's take a look at, well, let's just set things up here. So let's say the forearm is 2 kilograms, that's what they told us, and that there's this 5 kilogram sphere that the person is holding on to. Now, when we do the sum of the forces, So that's always a good place to start. The sum of the forces tells us that the force, all the upward forces, have to be equal to all the downward forces. And the muscle is lifting up, but mg is down, and big mg is down. And even the force of the bone needs to be downwards. And that's because if the muscle's lifting up here and the bone were lifting up too, this arm would just rotate. That's not going to support the arm. It's not going to maintain static equilibrium. So if I have, an object here that I'm supporting from below, I have to push down here to stabilize it. If I don't push down, that book is just going to rotate over. So again, if we have a force here lifting upwards, that's matching what the muscle is doing, I got to push down at that location. And so that muscle is going to have to be pushing up with enough force to offset the force in the bone, and to offset the force of gravity from the forearm, and to offset the gravitation force of the object. Now when I say force of the bone, it's the force of the humerus pushing down on the ulna. So that's going to be done with torques. So for this, we've got this force equation, that's fine. Maybe it's going to be useful at some point, but right now I don't know what FA is, I don't know what FB is. That's only one equation, it's got two unknowns. Forces alone cannot solve this problem. Now we've got to resort to torques, and so let's take a look at the torques and see how that would work. What I'm going to do is say the sum of the torques has to add up to be 0. Now when we set up one of these torque equations, we actually have to decide on an axis of rotation. Along what, relative to which axis of rotation are the torques going to be equal to 0. And I'm going to try picking this point, and then I'll come back and pick this point. Now, picking these points, we'll talk about why these are good points to think of as rotations occurring. If I'm starting with point A, in some ways that seems like kind of a natural way to think of rotations. The rotations naturally are occurring around my elbow joint. Now, I don't have to do it for that reason, but anyway, let's see what happens with the torques. So when I look at say all the torques add up to be 0, what I have to do is I've got to look at each one of these forces. I've got to look at force A, force B, mg, big mg, and ask how much torque is each one of those forces providing. Now, force A goes right through point A and has 0 lever distance. And that means force A is not providing a torque. So force A drops out of my torque equation, and that's why I picked point A to measure the torques. Because I knew that if I picked a point where one of my unknown forces was applied, that unknown force would drop out of my equation. So now what I'm left with is this. Let's pick that axis right there, axis A, and say that B, force B, has to provide enough torque in this direction to offset the torques being created by little mg and big mg. So I can see that FB by itself would tend to create what we call positive rotation direction, and little m and big M would tend to rotate the forearm downwards. So that's what we'll do. We'll take the force B, multiply it by its lever distance. Now in the diagram, if we take a look at the diagram, if you take a look at these homework problems, what they're going to have in them is they are going to have distances provided. So look, from joint A out to where force B is applied, that's 5 centimeters. Out to where the center of mass is for the forearm, that's 15 centimeters. And then out to where the golden sphere is being held is 35 centimeters. So what we'll do is we'll say that the torque coming from the muscle in the positive direction balances out the torque coming from the gravitational force on the forearm plus the torque coming from the gravitational force of the golden sphere. So now they gave us some nice numbers here to work from. This is 5 centimeters, this is 15, this is 35. So it was easy enough to divide through by 5. And so I divided this by 5 and divided this by 5, divided that by 5. And what that enabled me to do was solve for force B. So what that gave me then is 15 divided by 5 is 3 mg's plus 7 big mg's. So look at that. The muscle is not just providing the force mg and big mg. The muscle has to produce a tension that's 3 times the weight of the forearm and 7 times the weight of the golden sphere. That's a lot more tension than you would need if you were just simply lifting these objects up. If you just lifted an object up directly, it would just be mg. Why do we need so much force? And that's because the muscle is working with a very limited lever distance. Now the alternative to this would be that, you know, our arms and legs, and the muscles would be attached out here, and that would be awkward for our arms as far as, you know, where the muscles are located and how much tissue you might have to have. So in any case, that's what we're left with here. So calculating all that stuff up, FB is equal to 400 newtons. Now, what about the bone pushing down at point A? When we did the torque equation, notice that it could not be solved using forces. So I want to repeat that again, and the reason why is a lot of times students go, well, this torque stuff, it's kind of confusing. I think I'll just solve it using forces. Certainly any problem can be solved just by balancing forces, and that's not true. It's just not true. So you have to embrace torques. You have to look at the torques and go, all right, the torques are not so different from forces. When I'm using a torque equation, it's always force times lever, force times lever, force times lever. If I can get the lever distances correct and make sure that the directions of the torques are correct, you can solve these problems. So let's move now. Instead of measuring torques around point A, what if we chose instead to measure them around point B? So measuring them around point B, now this is just notation that I use. I say let's add up all the sums around point B and set them equal to 0. This time, if the axis is at point B, force A does have a lever. So the force A has a lever in this case, and that lever is going to be 5 centimeters. I can see that force A is 5 centimeters away. Now, if this is the axis of rotation, then force A is tending to lift the arm or rotate the arm in the positive direction, whereas mg and big mg are tending to rotate it the other way. So again, FA times 5 centimeters is going to be the amount of torque. And then on the other side, the lever distances have changed. Relative to point B, mg is located 10 centimeters away, and relative to point B, big mg is located 30. So the lever distances for this calculation, 5, 10, and 30, when we divide through by 5, we find out that force A needs to be equal to 2 times mg plus 6 times big mg, and that works out to be 333 newtons. Now, how much is mg? Well, the mg here, that's 2 kilograms, so if we multiply by g, that's about 20 newtons is all. So that's 20 newtons of gravitational force. This one's about 50 newtons. So 20 plus 50, we might guess 70 newtons of force would be needed, but that's not true. We need hundreds and hundreds of newtons because of the way the forces are working. All right, so again, you've got to learn how to use the torques. Make sure that you're practicing getting in and determining lever distances for these problems. All right, here's an example. If you have a force in your solution that comes out to be negative. So let's say here is I think this is an example in the book where it's a diving board. So here's a diving board. So here's one of the supports. Here's another support. Here's the diving board out here. Now it doesn't have a diver on it, but you know when a diver's on it, there's going to be a much, an additional force here that could be really large. Oh wait, this isn't a diving board, because that's 30 meters. That's a really big diving board, and that's 20. So it's something bigger. Now at first you might think that this point right here is supporting this structure, so it's lifting up and it's lifting up here, but that's not going to be true if the center of gravity is out beyond that support. So maybe this is an observation deck looking out over the edge of the Grand Canyon or something. And so if that's it, then 30 meters out, that's a long ways to walk over Grand Canyon. We actually need to make sure that this is being held downwards. If you think of what would happen if we have a support here, and then gravity actually is pulling from here, and maybe we have somebody over there, an additional downward force, those are all going to tend to tip the object or rotate it this way. So that would start to drop. An upward force here is not the correct direction. It needs to be in the other direction. Now you might panic then and say, oh no, I've got to get all the directions right from the start, and it turns out that's not true. So they're actually showing in this example, if you had decided to, and I guess we could have written this one up. We could have said this is just mg. They didn't give us a distance though. We would need this distance in order to solve this problem. But if you mistakenly drew the force in the wrong direction, the mathematics will save you. Because what will happen is, if you set up the diagram this way, FD turns out to be a positive number, which means you correctly picked the direction. But FA will turn out to be a negative number. And the negative signs just tell you you got the diagram backwards. The force is placed opposite to where it really is. And it's not a big deal, right? All right. So here we are again with this biceps problem. Let's go back and let me see if... Oh, here is the biceps. There we go. So here is the biceps initially, the one we looked at. And then I guess what we never did is part B. Sorry about that. So here's part B. Now, what happens if we have the arm rotate down? We can still come back to point A. And we come back to point A and look at all the rotations. This time, instead of the lever distances being 5, 15, and 35, they're 5 times the cosine of theta, 15 times the cosine of theta, and 35 times the cosine of theta. All right. So there's a factor of cosine theta that figures into all of these. Now the assumption here is that as this arm lowers, all of the lever distances decrease proportionally. They're all decreasing by cosine of theta. And when you look at the details as to the shape of the bone and where the muscles are attached, I'm not sure if that's going to hold up, but it's not a bad initial assumption to at least come up with an approximation. Well, it turns out with the cosine factor coming in on each of these, the force equations didn't change. You still need to have just as much tension. If this is really how things are configured, you would still need to have the same amount of tension even as you lower the object. So you're getting the same workout here and the same workout here. Now, those of you who are experts at physical training might know that there's more complications to this, and it's not this simple, or maybe it is this simple as an approximation. All right, here's another problem, one of my favorites. And so here is the bookstore sign. It's Arlene's bookstore. And so there's a sign located here. Now that doesn't look like, it looks like in the wind this thing's going to get blown around, but I guess this is rigid maybe. Here is a beam that comes out from the building, And the beams in statics tend to have hinges. So you might think, well, can't you just come in here with a bolt and just tighten the bolt down until it's really tight, and then it will just hold the sign up without this cable? And you could, but then all of the torque would be in that bolt. So more often than not, 95% of the time, instead of looking at the hinge and trying to generate all the torque right here, what we more often than not do is provide an extra support object. So here's an extra cable that they've put in to help support the sign. Now, what's the central object that we're going to be looking at here? The things that we want to solve for, they say, are how much tension would we have in the cable, how much force is there acting at the hinge, and then the gravitational force also is acting on the beam. So I think we go with the horizontal beam. The horizontal beam sounds like it's kind of the central object, and all the forces are being applied to that central beam. So, I drew kind of a crooked cable. Sorry about that. Cable needs to be straight. Tension in cable has to be right along the cable itself. So cables are flexible, and that means that if the force is acting kind of in a sideways direction, the cable will change its shape. So that's a handy feature of cables whenever we have a cable in a problem, or a string, or a cord, or a rope, that the tension has to be right along the cable itself. And so I've got a force of T acting on the beam, and I've gone ahead and written those as components. If you go back and read that recommendation earlier on, it recommended that we draw components of the forces, and it greatly simplifies the problems. Now the hinge also has forces acting on it, and since it's a hinge, it could have horizontal components and or vertical components. In general, there could be both vertical components and horizontal components of the force acting on the beam at the hinge location. And so what I've done is, it's a little messy here, but there's a T sine theta here and a T cosine theta here. Now with the forces at the hinge, I've got Fx and Fy, and that becomes completely general. So the force at the hinge is going to be some combination of an x component plus a y component. And so that should be completely general. We can go in and solve for those. Now, if I look at this diagram, and here's the sign. So there's a sign to, there's the beam, gravitational force acting on the beam, and the sign, there's a tension pulling down due to the sign, and that tension is going to have a magnitude of big mg. So that's our shortcut. Now, if I look at the forces in the x direction, this is kind of interesting. You might think, well, the hinge isn't really providing any force in the x direction, is it? But it is. And that's because the way the cable is oriented, the cable is going to provide an upward force, but the cable also provides a horizontal force pulling the beam towards the building. The building's got to be able to push back. If the building is not strong enough to push back with an equal force, the sign will push, the beam will push right through the building. So the building's got to be sturdy enough at that location. We can't just put that hinge anywhere. We've got to put it at a location on the side of the building where the building is sturdy enough to, well, here it is. The force that the hinge needs to push outward on the beam is going to be given by T cosine theta. Now in the vertical direction, we can do the same thing. What we can do is say all the forces up have to equal all the forces down, because it's statics, it's chapter 12. So that says that I've got upward forces of T sine theta and Fy, and those two components together have to equal mg and mg. Now this Fy here is a little tricky. I think it's going to be upwards. I'm pretty sure it's going to be upwards. This is one of those situations where, is it possible that it goes down here? I don't think it is, looking at the torques. I think it definitely needs to be up, but I don't have to worry, because if I pick the wrong direction, I'll still get, when I carry out the calculations, I'll get a minus value, and I'll know that I just picked the wrong direction. All right, so I'm going to keep these force equations here. The forces upwards balance the forces downwards. The torque, I'm going to start with point A. Point A worked so well last time, and by point A, what I mean is a location where some of these unknown values drop out. Notice I've really got three unknowns. I got to solve for three things here. I got to solve for the tension in the cable. I have to solve for Fx, and I have to solve for Fy. Now, by picking point A, Fx and Fy will drop out of the torque equation. That eliminates two of the unknowns. So when I write down the torque equation, what I can say is T sine theta is generating a positive torque. Mg and Mg are generating negative torques. The torque coming from T sine theta has to balance out the torque from Mg and big Mg. Now I can look at the lever distances. The length here was given as 2.20 meters. This is supposed to be right in the middle. I didn't quite get it drawn there. Sorry about that. The little mg should be right at the middle. So this distance is, the whole distance out here is L, and the distance right to little mg is 1/2 L. So I got a T sine theta times L for the lever distance from the cable. And then mg times 1/2 L equals mgl. Now, what about T cosine theta? Is that going to provide a torque? Now, the intention here is that the beam is small enough, we can treat the tension here as going right through point A. So we're going to say T cosine theta goes right through the axis, and it doesn't provide a torque because there's no lever distance for T cosine theta. So that's why it's not in the equation. So what I've done is I canceled out, factored out the L's, kept the factor of 1/2. I've got tension is equal to 1/2 M plus big M times little g. Now it's divided by the sine of theta, and that actually gave us 794 newtons, which is, that's quite a bit. If we go back and look at the masses, how much mass are we supporting? Well, that's 25 kilograms. If M is 25 kilograms, then mg is about 250. That's much more than 250. And then this is 28 kilograms, so that's about 280 newtons. So I've got, 500 and something newtons here, but we're using 800 newtons of tension in the cable to support the masses that we have here. So the tension's much higher than either of the gravitational forces. Now, we can also do this. We can, now that we have tension solved, we can come back up to our force equation right there, that top one, and say Fx is T cosine theta, and that works out to be 688 newtons. And that turns out to be much larger than the gravitational forces on the sign and the beam. So the building had better be sturdy, right? The building's got to be sturdy enough to hold the beam out, push it out with a force of 688 newtons, because that's what the cable is pushing the beam inwards with. Cable is pushing that beam. It's pulling the beam in with 688 newtons. Now, just as a check, so we've answered all the questions. Just as a check, what I wanted to do is go back in and take this equation here. Oh no, I guess we still haven't solved it. I take that back. So we do have to solve for Fy still, and we're going to get that from the second equation. So we started out the problem writing down some of the forces in X, some of the forces in Y. We wrote down equations for those. We couldn't use either one immediately. So we set them to the side and started working with torque equations. And then once I got that torque equation set up around point A and solved for the tension, then we were able to go back and use the force equations to get Fx and Fy. And that's kind of a typical way these problems get solved. So this is kind of a feel for these statics type problems. This is another very good example, I am going to say, to be looking at. Oh, and here's my very favorite. It's the ladder. So here is a ladder placed up against the wall. Now, what forces are acting on the ladder? It looks pretty clear that it's the ladder is the central object. It's the ladder that we want to be looking at and doing all the calculations for the ladder. And so let's see what we've got here. The ladder is leaning against the wall, and that means that there's a normal force of the wall pushing the ladder, holding it at that location. Right, so again, the wall's got to be sturdy enough that it can hold the ladder and prevent it from collapsing the wall. And that point of contact is 4 meters high. Now that's a normal force. There's another normal force right here. On the lower end of the ladder, there is a normal force. They've written it as a component, but I'm just going to treat it as, I'm going to start right with the components themselves and say, at the contact point on the floor, there is a normal force that's upwards. Normal forces have to be perpendicular to the surfaces. And so the surface here is the floor. And so that's what the normal force is direction of the normal force that we'll have. Now what's this force here? And that would be friction, right? That would be a frictional force that would be acting on the ladder on the floor. If we take away this frictional force, what happens? And you guys know, if you take the frictional force away, the ladder slides down, right? The ladder just slides right out. So don't climb the ladder if the frictional forces on the floor are suspect. Now, if there's friction down here, and there better be, and there's a normal force here, what about friction on the wall? And you could have friction on the wall. It turns out that for us in this problem, we're just learning how to do these statics problems. Adding a frictional force on the wall complicates the problem and makes it more difficult to anyway, we're going to ignore the friction. So we're going to keep the problem simple by ignoring frictional effects on the wall. But we do need the frictional force on the floor, otherwise there's no way to reach static equilibrium with the ladder. Now the ladder itself, we don't have anybody on the ladder right now, so we just have the gravitational force acting on the ladder itself, and that's about it. So what we want to do in this is, what do we want to do? They say the ladder has a mass of 12 kilograms. It's in contact with a point on the wall that is 4 meters, and then they've got this x naught thing listed as the distance away from the wall. Determine the forces acting on the ladder. So let's take a look and see what we have going on. Okay, actually let me come back here since they have such a nice drawing. The other item that I missed, that I just realized, is this very first piece of information. So always read the problem carefully. 5 meter ladder. All right. So you guys, you probably have seen so many triangles in your math classes. Here is a right triangle. The hypotenuse is 5 meters. One of the sides is 4 meters. What's the other side? And you can use Pythagorean's theorem, or you can just remember, oh yeah, that's a 3, 4, 5 triangle. So x naught is 3 meters. It's not a mystery number. It's 3 meters. So pretty quickly, since this is 5 meters and this is 4, we can determine that to be 3 meters. So let's just start from that. Here's our picture. So here is the picture of what's going on. Now this is the ladder. Notice I've drawn 2 diagrams, and I kind of like this approach. You guys could try it out and see what you think. But I drew one with the ladder actually in place. And then often the most difficult thing on these problems is determining all the lever distances. how do I keep track of all the lever distances? And it's very often that drawing a second diagram, which just shows kind of the geometry, at least for me, it allows me to more easily see some of the lever distances. So on this one, I've kind of emphasized this side is 3 meters, this side is 4 meters, and so if I look at mg, mg is going right through the center of that 3 meter line, so that mg line is going to be centered on the 3 meter distance. So let's do this. Let's look at all the forces in the x, all the forces in the y. If I look at this and I look at all the forces in the x, there is the frictional force and there is N2. And that's it. And what that does, you know, the statics, engineering statics tells us, is that these two forces then are the same. So the force of static friction on the floor exactly balances the normal force of the wall pushing out. Those two forces are going to have to be the same value. Now I don't know what they are yet, but that's a statement that I'm going to probably come back and use. In the y direction, I've got an upward force from the contact of the ladder on the ground. So I've got an upwards force of N1, I have a downwards force of mg. Now, these are not lined up with each other. In fact, since they're not lined up, they tend to create a torque that would tend to rotate things this way. But then these two horizontal forces, they're not lined up either. And so they're also going to create a torque. So it has to be that the torque generated from these guys matches the torque generated from these. So as far as the forces, N1 equals mg, N2 equals friction force. These are just some numbers that we want to keep track of. Let's move on and look at some torque formulas. Now, the point where the ladder rests seems like a good point to measure torques. That's where a lot of the unknowns are. I've got unknowns of N2, N1, and friction. And if I pick point A, that will eliminate N1 and friction from my torque equation. If I look at point A, the only torques I have are the torques coming from N2 and the torque coming from mg. And they're in opposite directions. So from the lower diagram, here's point A, I can see that the torque coming from N2, well, N2 has a lever distance of 4 meters. Here is the axis of rotation here. And N2, if I follow the path of N2, it misses that point by 4 meters. So I'm looking for where is its closest approach, where is the lever distance perpendicular to the force direction. Force direction is here, and that says from here to here is my lever distance, and that says it's 4 meters. Now for mg, I can follow the direction of mg. The point of closest approach is right there. And if I look along here, I can see that distance, the distance that mg misses axis, is 1.5 meters. So that's what I wrote. Oh, I didn't. Oh my gosh, I've done this wrong. Okay, you guys are going to have to correct this one. So N2 is at 4 meters, but mg is at 1.5. So that's going to be 1.5 meters, and well, let's see how the rest of this plays out. So what's going to happen here is N2 is going to be equal to not 3/4, but 3/8. So it looks like N2 needs to be 3/8 of mg. Check these out. Since we know what mg is, the mass is 12 kilograms, we can go in and calculate what N1 is going to be. So, but we are going to have to go back and recheck these numbers. So the mg value is good, but the N1 value is going to be different. Oh no, the N1 value is good too. So mg is good, N1 is good. What about N2? and that won't be. So I think that's going to be 3/8. Check and see. I think that's going to be 44 newtons. And then that would mean that the frictional force is 44 newtons. Now, the question might come up. You might be thinking, well, wait a minute. Couldn't I just solve this by using a coefficient of friction? And you can't. And the reason why is there's a piece of information that we don't know about the static friction, and that is, are we right at the limit? So unless the problem states that the ladder is just about ready to fall over, or not fall over, but if we're right at the point where the ladder is going to begin to slip, then we could set the frictional force equal to a coefficient of friction. But in any case, what I wanted to do was this. I wanted to say that in order for the ladder to remain stable, it has to be that the maximum frictional force is greater than or equal to N2. The maximum static frictional force is going to have to be larger than N2. Now that would say that the coefficient of friction then has to be larger than, coefficient of friction is defined as the maximum frictional force divided by the correlating normal force. So static frictional force here, that's correlated with the normal force here. So the maximum static friction force would be mu sub s times N1. And so that's what I've written down here. That's got to be at least as large. Now I think this was 3/8, so I think we can still follow this problem through. It's all a factor of 2 right here. So I know I'm going to lose some points. I'll lose like 5 points on that on the midterm. Anyway, I've lost the points. This is 3/8, so if this is 3/8 mg, and N1 is mg, the mg's cancel out. And it says that the coefficient of static friction needs to be, for the setup that we've got here, it needs to be at least as large as 3/8. And so 3/8 would be half of this, so that would be 0.375. So the coefficient of static friction needs to be at least 375. That's my prediction. Try this problem out and see if that's what you end up. That makes a lot more sense. I was a little nervous when I got this 0.75 because 0.75 is a pretty high coefficient of static friction. And you would think that the ladder maybe wouldn't need that much. Anyway, take a look. Now, you'll notice also, I should point this out too, if you want to think of this instead of a ladder problem, you could think of it as a bookshelf. You know, there's always this issue with bookshelves. This is what I always run into. I'm always going over to my books and putting them on the bookshelf and lining them up. And then, you know, some of the bookshelves during use, they get placed here, and then they slide a little more and they slide a little more. And then at some point, there's not enough friction to hold those books in place, and the books slide and fall down on the bookshelf. Same problem. So what we need is more friction on our bookshelves. But when you go to the bookshelf stores, when you go to the furniture stores, they have all these nice artistically designed bookshelves, when in reality they just need more friction. You know, we need more friction on the shelf, not less. Don't make the bookshelves all nice and smooth and shiny. Put a good, rubber pad along here or something so our books don't slide down quite so frequently. Okay, I've got to go back and get these numbers switched. How are we doing with time? I think we're doing pretty well here. We can maybe take a look at a few more of these. Stability and balance. So what we got going on here is a ceiling, and there's a tension in a cable, and here is the object. And if I look at the forces here, now they haven't labeled these. I guess I should have gone back and edited. Anyway, we'll edit them right now. This is mg, and this is tension. And so if mg and tension exactly oppose each other, that enables this object to be in static equilibrium. If we pull it to the side, well, tension now cannot possibly line up with gravity, and that's why we're ending up with a net force. So it becomes very important in engineering and other applications to identify when we're in stability and when we're not. This is a common example here, right? You go, well, the pencil, if I sharpen it and I place it right on its tip, shouldn't I be able to find the point where it completely balances? And you can, but it won't stay there. So objects are in unstable, what we call unstable equilibrium. It's in equilibrium, but it's not stable, and not stable means if it tips just a little bit from its equilibrium point, there is no force to bring it back. So two things can happen. If we've got something like this, it could be that when the pencil starts to go to the side a little bit, there is some kind of a natural restoring force that brings it back. That's not the case for this pencil. So for this pencil, once you shift away from the equilibrium point just a bit, the forces guide you away from static equilibrium. So it's not going to go back to static equilibrium, it's going to fall over. And I guess form a new static equilibrium with it falling over sitting on the table. So equilibriums are not necessarily stable. Here's a refrigerator, and the two forces acting are the normal force and the gravitational force. So here's N, here's mg. Now, as long as those two forces line up with each other, there's no torques. There's no tendency for this object to start rotating. Now, if I push the refrigerator up so it's resting on this corner, what has happened is it's still in a stable equilibrium, I guess. It's still going to tip back onto its feet because the gravitational force is still on this side of where the normal force is, so the torques will rotate the refrigerator back. But once we've tipped it far enough that the center of gravity moves past the point where that normal force is, there's no longer a way to balance it. Okay, the refrigerator is not going to be balanced. It's going to rotate the opposite direction, and this is probably a direction you don't want the refrigerator to rotate. Although, rocking it back on its feet here, maybe that wasn't a good idea either, but at least it's sitting upright. Anyway, that's the idea, is identifying where those points are going to be. Here's another good example. This is, the ergonomic argument for backpacks versus carrying bags around. If you're carrying a heavy bag, then the center of gravity shifts over to one side, and as a result, you end up leaning your body to compensate for that effect. So you have to lean over to bring the center of gravity back over where your feet are located. So with a backpack, you can keep the center of gravity more centrally located. It does move backwards, but you can lean forward a bit, I guess, to offset that, which ergonomically is supposed to be better. Maybe you should load the front and the back, have a front pack and a backpack to keep the center of gravity where it's easiest to compensate for. Okay, this is kind of the next part of the chapter. So we're through the first part of the chapter, all that stuff on statics. Take a look at the problems. This is really an important area of physics and engineering, and it does take a little practice getting a feel for how the lever distances work. Once the lever distance stuff falls into place, I think you're going to be good on these statics problems. Any questions at all, stop by, let me know.